Okay, hello everybody, and welcome to tonight's live stream. I suppose the title for this is Why is it in black and white? And that's really because tonight I put out my kind of normal kind of weekly video on YouTube. This was one that I filmed last week when I went down to London for the day, and I met some amazing students who'd done really well in various kind of challenges and things that the British Physics Olympiad are putting on. The video I actually filmed, I did it in colour as normal, but then I kind of messed up the settings, like the auto setting when I filmed. So I thought it would be better to actually do it in black and white if I just show you what's on the screen. And the only reason it's not in colour is because I couldn't quite get the colour grading right. It looked like too orangey, a bit washed out. And I thought, you know what, in black and white, actually all of the colour looks a lot better. So this video here, I interviewed various people, and if you want to find out their advice, and this is from some people in year 13, plus some year 12 and year 11 students later on, you can see about their kind of tips for using past papers to kind of sort of study effectively. So if you haven't already seen this video, you can watch it after you've watched this live stream. Now tonight, as normal, we're going to be doing some GCSE stuff and A-level. We've got GCSE from 7:30. And then at 8 o'clock, we're going to be going on to A-level. I know a lot of you at the moment are kind of watching the GCSE streams and even more people watching the A-level. But what's really nice is that so many people are catching up, either finding stuff on YouTube afterwards or going to my website to actually see the resources as well. So if you want to know why that the video is in black and white, I basically messed up my settings when I filmed the video that I released just earlier today on YouTube. But you can watch that. It's all about the best exam advice. Right, let's just get going straight into the GCSE stuff. So the first one is a question to do with refraction. And you'll notice that if you've been watching many of these streams, and I know there's lots of people in the chat, some new people as well, so 78J, good evening, welcome to the chat. So this one over here, the first thing should look familiar to you. We have air, we've got a glass semicircular block. Hi Joshua. And they shine a ray of light through the glass block at different angles and measure the angle of refraction. Now, why is it in physics that we have, you know, these kind of semicircular blocks, which I think are only ever used in physics classrooms? Well, the reason is if we think about what's going on, when it meets this flat surface here, there's going to be the change in direction because this is meeting that surface at an angle. When it meets this surface over here, because this is a semicircle and this is meeting the very centre of that semicircle, then it means that here the angle of incidence is going to be 0 because this is equal to the normal because this is at 90 degrees to the surface, and this also leaves at 90 degrees to the surface. So that means the angle of incidence and the angle of refraction is 0, so it just passes out here in a straight line. Or equally, if you were to shine light at the very centre over here of where the circle would be, when you shine light in, it just goes straight through and it doesn't bend at that point. So measure the angle of refraction in figure 9. Okay, so this one here is easy marks. Again, I would say, as I've already done many times, you need your protractor, you need a pencil. The angle of refraction, well, that's going to be the angle of incidence over here. So this is going to be the angle of refraction. The first thing I'm going to do is very carefully putting the centre of the protractor on the centre point over here, is I'm going to mark on 90 degrees over here. And that means I can then connect up this normal line. And if I just do that, we should get, and I just by convention we tend to use a dotted line, and this normal line is at 90 degrees to the point on that surface where the light is entering, and then we just need to use our protractor to measure the angle, and I reckon this is equal to, I'm going to do it this way round, I'm going to start here, go round, and that to me looks like 14. Okay, so the first one is this angle is equal to 14 degrees, and that's because this angle in here is the angle of refraction, the angle over here is the angle of incidence, okay? And it's always between the ray of light, or the wave, and the normal line that we have these things here. And what you'll see here is that the angle of incidence is greater than the angle of refraction, and that's as it slows down. And that's why we often say the light bends towards the normal. Okay, there we go. The next one, I want you to have a look at this table here. This is not as straightforward as you first maybe think. So identify the anomalous result. So looking at the table here, everybody in the chat, Ramaisa, Zaidi, we've basically just done the very first part of this question here. We only started about 5 minutes ago. So that's the first one. It was just a case of measuring the angle of refraction. I want all of you to look at this. Which of these results here is the one that you feel could be an anomalous result? So the first, somebody's saying 14. Right, the first one. 40 incidents, 23 refractions. So we've had 2 people say that. We've had 1 person say this. Some people say 40, 23, 40, 40, 14, 14. Okay, this one here, this is good. Right, let me just measure this angle over here. Oh, actually, is that right? Actually. Yeah, that could be it. Okay, this one here, I reckon that looking at these, we go up by a factor of 7, we go up by 2, then we go up by 10. So what we have here is, even though the angle of incidence goes up by the same amount each time, and that's the kind of thing which is going to be our independent variable, that's the thing that we're deciding to change. So this is the thing that you're in complete control of. That's the thing that we then measure, that's our dependent variable. And I would say that looking at these, this one over here is the anomalous result. Okay, but I think this question again is harder than GCSE. At GCSE and even at A-level physics, especially in exams, they always make the anomalous result really, really clear. Now, the reason I think that the one which is anomalous is 20 going to 14 sounds about right, 30 going to 21, and I reckon this one here, it's not going to go up by 7, but we can see there's like 12 between the two, so I reckon this one should maybe go up by 6, up to maybe like 27, and then it goes up 6 again maybe. It's difficult to tell. They're basically all going up by about 7 each time, but this one isn't. So I reckon this one here is too low. Okay, so I reckon 23 would be the anomalous one. And what it's important to do is, maybe circle that in the table and write down your answer so it's really, really clear. So yeah, but I reckon you can see here that that goes from 21 to 23, and that goes from 23 to 33. So that goes up by 2, then it goes up by 10. So I think that one there is lower than it should be. Yeah, that is a tricky one though. Thank you to Sinister Llama. That is an awesome name. There's so many people here who've got great names, but Sinister Llama, that is a good one. Okay, so that one there is just a case of identifying the anomaly. And of course, you know what to do is if you have an anomalous result, you need to identify it, and then you need to discount it from calculating any means. Okay, the next one then says, the student thinks that they may have positioned the ray box too far away from the glass block. Explain the effect this could have had on the results. Now what we have here is a diagram that's got a perfectly straight line that meets this, and then it all bends like this. Now, of course, if you've actually done this practical where you've had like mirrors or ray boxes and you're looking at refraction, often you get kind of like a spread of light that kind of, because it doesn't always come out in a perfectly straight line that's really kind of narrow. Instead, what tends to happen is the beam kind of sort of diverges slightly. And that means rather than meeting this boundary at a point, it kind of spreads over a certain area. And of course, the further away the light source is, even though it might only spread out a little bit, it's going to spread out more and more. Okay, so we've got people like Slow-Mo saying that the light could be more faint, meaning the accuracy of the angle is affected. Yeah, so we could say that one way is that maybe the light gets too faint, even in a darkened room. So it could be that light gets too faint, or you could say that maybe the light is too spread out. And of course that means then it's going to be difficult to see exactly where the centre of that ray of light is. And then that's going to then affect the accuracy of the results. And because for this one over here, what we're using is a ray box. That means we're not using a laser, so we don't have this coherent source in a perfectly straight line. We're using a normal kind of maybe incandescent or filament light bulb, and that means the light's not going to be great. So the light gets too faint or the light is too spread out. And then you could say that this makes it difficult to identify the center of the light. So it's harder to measure the angle accurately. Okay. Somebody's saying that these GCSE papers with margins look so ugly. Well, that's what exam papers look like, isn't it? They just look like this, where you've got the margin. You shouldn't write outside it. There's often a barcode at the bottom with the page number on it. Suggest a way other than moving the ray box closer in which the student could improve their investigation. So one way, and I think there's loads of things that you could have for this. The slow-mo guy says use a laser. So one way is you could use a laser. And if you do that, that's going to give you a definite kind of straight line that doesn't spread out. Right, feather. Can you say the light is less concentrated? I reckon we don't really tend to talk about the concentration of light. I mean, that's a good word for chemistry. Instead, we maybe talk about the light intensity being lower. So if we're talking about light, the word concentration doesn't tend to work with that so well, but the word intensity is much better. Use a stronger light source. Joshua, stronger. Again, I think maybe strong is more of like a chemistry word if you think about acids and stuff like that. I would say use a more intense light source, or more powerful. So if it's more powerful, then there's going to be more energy being transferred per second. More powerful light source. But of course, then the danger is it might start to get really hot. Now, the other thing, we've got taking the brightness of the room into account. Ren, excellent. Yeah, that one could do it. Matty talked about using a smaller opening, so you might get a thing there. So a lot of this stuff here is about the way that the light could be better. But there's also, let's look at the table over here. This table is not the kind of thing that I'd expect from a GCSE student. First of all, the angle of incidence, we've only got these things, but why not have 10, 60, 70 and 80? So one thing we could do is we have a greater range of results. And if you've got a greater range of results, that means you're going to have a much better set of data to actually plot some graphs from. The other thing that we need to have is we need to have repeats. So maybe if you repeated it, you might get something like 14, you might get 21, 26, 31, then you do it again, and you might get like 13, 20, 26, 30 maybe. And if you do that, you then realise that this one is definitely an anomaly. So we're talking about repeat the experiment, take an average, as Ren says. James Stevenson, excellent thing, higher intensity light source. So there are lots of things we could do. So we could use a laser, a more powerful light source. We could increase the range of I, and that's just going to be my angle of incidence. We could talk about repeats. We could do it in a darker room. And what you'll find is that when you have a question that says suggest, there's often many things that you could actually say, and all of this stuff here is just basically kind of common sense. Right, maidenless. Can gradients have a unit? Yes, they can. So for example, if you look at a graph, maybe we've got a distance time graph, and you're looking at the journey of an object, maybe something like this. Okay, if you were to work out the gradient of this line over here, and of course you do that by drawing a big triangle, we've got the distance measured in meters and we've got the time measured in seconds. And to work out the gradient, which is dy by dx, you're going to have the change in s, which is in meters, and that's going to be divided by the change in x, which is in seconds. And therefore the units of that gradient would be meters per second. So yeah, gradients can have a unit. Why wouldn't the light still spread in a darker room? Matty, that's a good point. The light would still spread out in a darker room, but it might be easier to see exactly where the centre of the ray of light is, because you've got a greater definition between like a pitch black room and the ray of light. Maybe if the light, the ambient lighting was still fairly high, you know, if I had a ray box here now, it might be a bit more difficult to see because there's not that contrast. Right. Write a conclusion for the investigation and explain why the light behaves like that. We could basically say, and this is based on the data, we could say that the greater the angle of incidence, the greater the angle of refraction. But then we could also say, but the two are not directly proportional. In actual fact, if we looked at a graph and we had angle of incidence here and angle of refraction, what we'd see is a line that looks a bit like that. So what we can say is that R is not proportional to I, or I is not proportional to R. So they're not indirectly proportional either. They still both get bigger. So we can see that that gets bigger and this number gets bigger. So they are still related, where when the angle of incidence is bigger, the angle of refraction is bigger, but they are not directly proportional, because you don't double from 20 to 40 and then, or you don't double from, like, say 25 to 50 or 30 to 60. That doesn't double that either. In actual fact, if you actually look at it, we find that sine I over sine R is equal to a thing called n, which is our refractive index for any A-level people watching, and that means sine I is proportional to sine R. So you've got to take the sine of each of these angles and then they're directly proportional. Okay, slow-mo, don't worry about it, that's all fine. So the conclusion for the investigation: why does the light behave like that? We might say that the light slows down as it passes from air to glass and bends towards the normal. Okay, so basically it's because the light is slowing down, that's why these angles are changing. And yeah, that one there I think is more than good enough for GCSE. A good question from Ramesh Zaidi. Is there any topic in GCSE physics that students lose a lot of marks on? I think generally students lose marks everywhere on silly little mistakes throughout a whole paper. I think the ones that people tend to find most difficult tend to be stuff to do with like electromagnets and transformers, especially if they're doing triple science in paper 2. But I wouldn't say that there's one bit that everybody gets wrong all the time. I think motors is difficult to describe how a motor works in terms of things like the you've got like a split ring that kind of rotates, and you know which way things going with Fleming's left-hand rule. So I definitely think sort of the electromagnetism part of paper 2 is one of the more tricky areas. Okay, right. So this one over here is a question about refraction, but now we're looking at sound. So it isn't just light that refracts. Other types of wave, including sound, can also refract. Okay, so another student investigates how sound waves are refracted by gases with different densities. They've got a microphone, they've got a timer to determine the speed, and they find that the denser the gas, the faster the sound wave. Describe what happens to the frequency and the wavelength of the sound wave as it travels into a denser gas. Now for this one, I'm just going to write down the wave speed equation that says V is equal to F lambda. Okay, now when you have refraction, what we do is we change things like the speed of the wave and we change the wavelength, but the frequency stays the same. So the first thing we can say is that as this wave of sound is refracting, we can say that the frequency stays constant And I would urge you just to write the word frequency in the exam rather than this kind of sort of shorthand way I'm doing that at the moment. So the frequency would stay constant. Now it says here that the faster the sound waves in that denser gas. So we already know that V increases. But of course, if V increases and the frequency is the same, we can also say that if the frequency is the same, then the wave speed is going to be proportional to the wavelength. Okay, so the wave speed depends on the wavelength, and if it's got faster, that means V's got bigger, and that means the wavelength increases. Okay, right. Does that explain redshift? No, this is like a slightly different thing to redshift. How do you work out that frequency was the same? This one over here, I didn't work it out. That was just some of my knowledge. So imagine you had, like, let's go back to the light example. We've got maybe a block of glass and you have a red laser. You shine the red laser light into the glass and you'd see this kind of red beam. It would bend towards the normal and then it would sort of come out the other side. So it looks a bit like that. Now the fact it's red is because of its, also the reason it's red is because of the frequency of light. Okay, so the frequency determines the colour that you see. And of course, if you put in like green light, so you shined a green laser into this, you'd see this kind of green laser light. And the colour depends on the frequency of that. And that means the frequency stays the same. What's changing is the speed and the wavelength. So for this one over here, this is just a kind of thing that I know, and you all know as well now. So when refraction happens, we still have the same number of waves passing per point each second. The frequency stays the same, but if we're going faster and V increases, then that means the wavelength must increase. Okay, right, yeah. Okay, so I think that question there was all right. Okay, let's do some stuff for the next 8 minutes for GCSE. We're going to whiz through a few bits of this question. So this question here is about Newton's second law. Tick the box that corresponds to the incorrect statement out of the following. So let me just put these down as A, B, C and D. It'd be great to... So now I'm doing this question which is about this kind of acceleration practical a lot of you might have done. Which of these is the incorrect statement? Now, for something like this, I think it's quite useful to kind of try and get all of this stuff here into like shorthand. So the resultant force is directly proportional to the acceleration if the mass is constant. So what we're saying here is that the force is proportional to the acceleration provided that the mass is constant. And that's true because we know that F equals ma. So if the mass is constant, if you had a bigger force, you'd have a bigger acceleration, or a bigger acceleration is caused by a bigger force. So that one there is correct. So it can't be this. Mass is inversely proportional to constant resultant force if acceleration is constant. So here we're saying that m is proportional to 1 over f if a is constant. Is that right? Mass is inversely proportional to that. So actually, is that right? I'm not sure. Okay, I will be doing AS in a couple of minutes' time, I think at 8 o'clock. Right, the next one, acceleration is directly proportional to force if mass is constant. Well, basically, if force is proportional to acceleration, then acceleration is also proportional to force. So here we said that the acceleration is proportional to the force for a constant mass. And again, we know that F equals ma. So that is a correct statement. And then mass is inversely proportional to acceleration. So we're saying that the mass is inversely proportional to acceleration if the force is constant. And effectively that's saying the mass is equal to force over A. So a constant force, mass is inversely proportional to acceleration. That's also correct. And therefore this one over here is the incorrect statement. So that's the box you tick. Loads of people get that right. So Matty, we've got the slow-mo, Joshua, excellent. B is incorrect, Joshua, excellent, good stuff. So that one over there is just that process of going which ones are definitely wrong and trying to narrow down your answers. Okay, it says the student decides to vary the resultant force on a cart and measure its acceleration. So what we're looking at is a relationship between force and acceleration. So that's what they're going to investigate. They're going to change this. So this is our independent. And then they're going to measure the acceleration, which in this case is the dependent variable. And that means the thing that we must keep the same, the control variable, is the mass of that cart. So that's going to be our control. Now, how many people have done this experiment where you've got a cart, you've got a mass hanger that kind of hangs over the edge of the bench, you let it go and that accelerates. How many people watching this have actually done this experiment? Okay. Right, so I can see that a few people have done it. Me, did it in school, I've done it, I have. This is good, this is really encouraging. Oh, no, somebody hasn't done it. Okay, Feather, yeah, you did it, awesome stuff. Yeah, loads of people have done this one. Now, if we're going to change the force, we're going to do that by adding more masses onto this. So that's going to change the force. So this is basically the force that is acting down, and that force is going to cause all of this to accelerate, and we're going to measure the acceleration. How do they make it a fair test? Well, what they need to do is they need to keep the accelerated mass constant, okay, and the thing that accelerates is basically this cart, the mass is on top, which I'm going to colour in red. There's obviously this bit here, that's like for holding something later on. This is going to accelerate as well, because that's getting faster. That gets faster, and so does the bit of string that goes over that pulley. So everything in red here, everything that's red is all accelerated, and that's the mass that you must keep the same. So you need to keep the accelerated mass constant by moving the masses from the cart to the mass hanger. So what that means is if you want to make the force bigger, what you need to do is you need to take one of the masses off the top here, and you take this mass and then you hang it on that bit over there. Now what that's going to do is going to change the size of the force which is causing this to accelerate, which is then going to change the acceleration of everything, but the total mass, which is everything coloured in red, is all going to stay the same. And that means as you add more masses onto this to make the force bigger, because the force is provided by the weight which is hanging vertically down, then you're going to basically be taking stuff from here, adding it onto this each time, and that means the total mass of everything that accelerates stays the same. Okay, so what you're not doing is just leaving this and just adding more masses from a different mass hanger onto this. Anything that you add to this must come off this, or equally, if you take stuff off this, you need to put it back on the cart. And that means we keep the mass of the accelerated thing constant, and that's going to then give us this link between the force and the acceleration. Does that make sense? Okay, I reckon we'll leave it there for this evening for the GCSE. I just want to kind of really make that clear that when you've got something where you're changing the force, measuring the acceleration, you've got to keep the mass constant. Now the other variation of this experiment is basically where you change the mass, so that would now be your independent. You look at the acceleration, which is your dependent, and what you do is you keep the force constant. And that's the time where you have the same number of masses hanging the edge, and all you do is you take masses from a different pile, you put it onto the cart, and you're just loading up the cart to make it heavier and heavier. And then you can see that basically if you've got the same force on a heavier cart, which is more massive, the acceleration is going to be lower. Okay, so these are two separate investigations that you can do, but using the same equipment. Okay, hopefully that helps. Right, do we have any last minute GCSE questions in the chat? for the last sort of 30 seconds or so before we go on to the A-level stuff. The slow-mo says you don't really understand inertial mass. I would say don't get too hung up on it, apart from, I suppose, really that the inertial mass is basically the mass that just wants to keep going at this kind of constant velocity, or it wants to stay still, and you have to apply a force to it to cause that acceleration. Okay, right, I think we've kind of done for GCSE. For anybody now watching, do let me know in the chat if you are A-level students. It'd be great to know, and obviously say hello, introduce yourself, which exam board you're studying for your exams this year, and if you're in year 12 or year 13. So thank you to everybody who's just been in the GCSE chat. Let me know. Matty, no problem at all. Thank you. Lifesaver, thank you very much. Thank you. Right, we now have A-level AQA, AS student EdXL. We're going to be doing some stuff that is suitable for AS students as well tonight. OCR A-level physics, OCR year 13 EdXL unit 2, year 13 OCR A-level by A-level student AQA. Yes, I think there's a whole mixture. Now, again, what I'm trying to do with these streams, hello Jamie, hello GVK, is I'm trying to make sure that the stuff I do is suitable for everybody. And that means if you're year 12, you can follow along. I'll teach you some new stuff. But this is still going to be really useful if you're doing OCR, year 13 stuff, if you're doing AQA stuff. It's basically the essential core physics kind of skills that everything else is based on. Okay, now a lot of you, actually even some of the GCSE crowd who might still be here, might recognise this. Okay, Jamil, any tips for AQA multiple choice questions? They seem really hard. Yeah, basically, I would say, although you will be practicing lots of multiple choice questions when you do past papers, the way to get really good at multiple choice questions is just to do lots of longer answer practice paper questions as well, because that will just deepen your knowledge of physics. It will give you that good grounding in how to answer questions. And ultimately, if you know more about the physics and you understand it more, it's going to be easier when it comes to doing the multiple choice questions. Okay, should you do them at the start or the end of the exam? I would say I'd whiz through them and do the easy ones at the start of the exam. So if you know it's like a 30-second question or a minute-long question, get it done. If it's taking you 2-3 minutes to do it, it looks a bit challenging, you're not quite sure, then come back to it at the end when you know you've got the time to do that. Okay, but that would be my thing. Right, so the force exerted by a straight wire in a permanent magnetic field was investigated as the current through the wire was varied. The wire was firmly clamped in position above a mass balance as shown below. So I suspect a lot of you watching this will have done something like this, where you basically have this wire. Often the setup I've seen before, if I try and draw it in sort of 3 dimensions, is you basically have a wire that looks a bit like this. Okay, down here is where you have the kind of magnetic field. Well, that's not drawn very well, is it? Okay, so you've basically got the magnets down here. This is on like a yoke or a cradle, and the wire kind of goes through the middle. This is then on top of your mass balance. So that's the mass balance that's going to give you some kind of reading. Oh, I've not drawn that very well either. So basically this is your mass balance here. And then what you do is you kind of clamp these in positions using retort stands. Something a bit like that. Okay, so this is completely clamped. And that means it's quite easy to change the orientation of the wire. So you can change the angle within a certain thing. And also you can change the length of the wire that's in it. So you often use quite a thick rod. And this one here, the slow-mo says, yeah, it's basically the GCSE F equals BIL. And this is something that's investigated further at A level. Okay, now the first question. We've got all of this set up. We'll come back to that in a second. Describe the difference between a Magna-Dur magnet and a conventional bar magnet. So, if you've done this before, what's the difference between this setup and just using a bar magnet? So these are Magna-Dur magnets. What is special about them? So let's see what people think in the chat. This ain't an OCR, is it not? Or what? Okay, this is kind of why I'm doing this, to kind of sort of teach you some of the kind of the things that I didn't even realise till several years of teaching. Now basically, if you have a normal bar magnet, I'm going to draw this magnet like this. Okay, and what we might have is the north end and the south end. Okay, I always forget which one is painted red. Okay, but let's say we've got the north end and we've got the south end. So I'm gonna colour the south end in red. Okay, so this is like your normal kind of bar magnet, and from a bar magnet, the field lines are going to go from the pole to the pole. So here, if we were to draw the field lines in, they'd come from the north pole around to the south, like this. They'd obviously be doing this in kind of all 3 dimensions. So what we have are the field lines going from the north pole down to the south pole. And this is kind of like my 3D thing there. Okay, is north red? I think probably north is red, but let's just go with it like this. We've got the north end and we've got the south end. Now, sorry, nice. What is this, unit 2? What unit is this? Nice, sorry, I missed your comment. I don't know which unit this is for that board, but basically this is a question about Fleming's left-hand rule, okay, and the force on a current carrying conductor in a magnetic field. Okay, right, this is a bar magnet. Now, a magnetar magnet, it looks similar, but basically, if I was to draw the magnet, and they're like a similar shape, but what they have is basically one side, this whole face here, is basically the north face of the magnet, and this side here, I'm going to go by convention from what I did there, I'm going to say that's the south face and this is the north face. Okay, and that means we've basically got the poles along the long flat side of that magnet. Now if you have 2 of these quite close to each other, you can see what's going to happen here, can't you? Okay, we're going to have maybe, again, that's going to be like the same side, like this. Okay, and now we'd have the field lines going from north to south, if you put them like this. So basically the poles aren't at the end of the magnet, like where you have a bar magnet. The poles are along the big flat face. Okay, now what that means then is, imagine this was our magnet. Let's imagine we had like a north pole on this flat side, and because the pole is on the flat side, these magnets stick to this kind of metal steel yoke, and also that then means that we're going to have this uniform field, a uniform permanent magnetic field between the faces of the magnet, and that means we have this uniform field that the wire is going to be moving through. Okay, am I doing AS at 8 o'clock? Yeah, this is kind of AS physics so far. This first question though is basically something that everybody should know if you're doing A-level physics, including all of you in year 13. If you instead had just a bar magnet stuck to each side, well, they wouldn't stick and you wouldn't have this uniform field in the middle. So again, what I've tried to draw here is kind of this magnetic field, because what we have is like the 2 different faces of that magnetar magnet, like this, and then we have, of course, our this kind of uniform field. We've got a current going through the middle, and then we have a force going up or down. Okay, Scarface, that makes sense. Yeah, I think it does. Right, the next bit then is the following data was recorded. We've got the current that's actually going through the wire. We've got the reading on the mass balance in grams, and we want to know the magnitude of the force. Now, effectively, when there's no current flowing, this reads 151 grams, which means that the mass of the yoke is 151 grams. Okay, now when we have a current of 17 milliamps, what we see is that the reading gets smaller, and as we have a bigger and bigger current, the reading gets smaller. And that's because this is going to be fixed in position. There's going to be an interaction between the permanent magnetic field and the magnetic field then that is around the wire when you've got the current flowing through it. The magnetic fields interact, and basically this is going to cause a force which is basically going to be pulling this up. Okay, so there's going to be an upwards force acting on this, and that means this number here is going to go down. So how do you work out the magnitude of the force? Well, of course, we know that this is the reading on the mass balance in grams, and we also know that I was going to write it over here, that the weight is going to be equal to the force, which equals mg. So to work out the force, we need to look at the change in reading and times it by g. So here, what we've got is the change is equal to 2. Okay, and it's just the magnitude, so we don't need to know about the direction. What is the name of the standard that's holding the balance that sounds like yoke? Yeah, it's just a yoke. It's just sometimes called a yoke, which is another word for something that holds something else. So it's just a metal yoke. Yeah, there we go. Scarface, I think that's what it's called. Okay, so it's changed by 2 grams. So that's 2 times 10 to the minus 3 kilograms. Multiply that by 9.81. And 2 times 10 to the minus 3 times 9.81 is 0.01962. So I guess I'm going to give that to 2 significant figures as 0.020. It was 151, it decreases to 146, so it changes by 5 grams, so 5 times 10 to the minus 3 times 9.81 is 0.049. And of course we can go along, and this one here is then something that even people doing AS physics can do. And this just means that we get these numbers. I have worked out these previously, so hopefully these are good. 0.137. Okay, is that right? Yeah, okay. Why does the reading on the mass balance decrease as the current increases? Well, basically when you've got a bigger current, because we know that F equals BIL, so even if you are year 12 and you haven't been taught this yet at A level, you still remember this hopefully from GCSE. Leela, just to confirm, the bar magnet will not create a uniform field, but the magnetar will. Yes, that's correct. So the magnetar will create a uniform field between them. Let me just get some actual magnets. Okay, people are right. It's the north end which is red. Basically, if you have bar magnets and you hold them end to end, there will be a uniform field between the two things, going from the north to the south pole here. Okay, we can sort of ignore the other poles. Now the magnetar magnets tend to be set up like this, and you have the wire in the middle. But of course what we want is we want this whole face to be a north pole and that whole face to be a south pole, and that means we then have the field lines kind of going across the ways from this one to this one. If you just put 2 bar magnets side by side, all we'd get is again this kind of field going around from the top to the bottom, and it wouldn't be a uniform field between them. Hopefully that's kind of making sense. Okay, so we know that what we could say is that explain why the reading on the mass balance decreased as the current increased. This is because of the force on the yoke due to the current in the wire increasing. Okay. Okay, in the practical that somebody else did, G. May says, when they did it, the force from the magnetic field acted upwards, the mass on the scales increased. Why is that? Is it due to an equal and opposite force? Yes, it is, G. May. So basically, effectively, if you've got maybe the current going in one direction, you know, think about Fleming's left-hand rule, imagine we had something like this. We'd have magnetic field, we'd have current here. Now, depending if the current was either going this way or this way, you'd either have the reading here increase or decrease. Okay, and I suppose really what I did there is I really just wanted to look at the magnitude of the force. So we're looking at the relationship between current and force. Okay, so Madam Pinky, a great name for actually describing something to do with hands and fingers. So Fleming's left-hand rule is just a simple way to look at the force that's due to the current in a current carrying conductor. So the first finger points in the direction of the magnetic field from north to south, The second finger points in the direction of conventional current, which is positive to negative, and then the thumb shows the motion or the direction that that wire, for example, would move in that field. Okay, and this is when we have all three things acting at right angles to each other. Okay, right, the next question says, complete the table, plot suitable data on the graph above. So we've got some data. This shouldn't take me too long to plot. So we've got the current in milliamps. So when it's 0, that's 0. When it's 17, this is 0.02. So this is going to be 15, something like that. 34 and 0.049. I think it's something like that. 50 and 0.59, is that right? Something like that. 72 and it's going to be 0.098, which is like there. Obviously I know you do this better in the exam. We'd have 89 and 0.128, so that's going to be roughly about here. And then we've got 98 and 0.037. Like that. Okay, so what we have is kind of like real life data, as in it's not perfect. Okay, Riptide Kills, again, great name to have here today. FBI, Tommy, yeah, you've got the force, you've got B, the magnetic field, and I, the current. So FBI is a really good way of remembering it. Okay, so FBI, cool. Like a gun that you're kind of holding people up with. Okay, so complete the table and plot suitable data on the graph above. So what we have here is, I reckon, a pretty good straight line. Do you reckon? So I reckon, again, this is, I've printed out an A3 to make it big enough for everybody to see tonight. But we've definitely got a line that goes through the origin. We've got maybe some points above and below it. I reckon that one there's a bit of like an anomaly, so I'm just going to kind of ignore it a bit and discard it. And I'm going to put a line through it like that. Okay, I guess we've got a point above it and a point below it. So there we go. So I think what this does show is that the force is actually proportional to the current, and therefore F, this leads on to F equals BIL. Or does it? Well, what we can do is we can investigate other factors that could affect the size of the force exerted by the wire. So what else would maybe change the force that's felt by the yoke? If we look at this equation over here, we've investigated I so far. So something else you could investigate is B, the magnetic field. But the difficulty with that one is it's often difficult to actually quantify the size of that field. Okay, so that's quite a difficult thing to actually vary. One way you might do it is, again, I'm going to do like my 3D picture, is sometimes you have like the yoke that looks a bit like this. Okay, you obviously clamp on your Magnedur magnets on the side, so you might put one on the inside that goes in there. To make the field stronger, you might put another one that kind of goes on the outside here, so you kind of start to have 2 magnets each side, or maybe you even have 3 magnets. But it's very difficult to get a good range of readings, and it's also difficult to know that if you add another magnet, are you actually doubling that field or not? So it's quite difficult. The other one, Iris, length of wire. Yeah, so we've got L over here. So we might talk about the length of wire. And the way that I've done this before in school is that you basically have a piece of wire that's like this, and you have another piece that's got a bit of a longer loop at the bottom, and then you can basically change the length of this. So you clamp this bit each time. This bit here is inside the magnetic field at the bottom. This bit here, because that's not at 90 degrees to the field, you basically don't really get any up or down force. There might be a force side to side, but not up or down. Okay, so we could look at the length. And of course, the other thing we might look at is the angle. So if we had a top-down view of this, so maybe this is the yoke, and we're kind of looking from the top down. You've got your Magnedur magnets in here. What you might have is a way to actually change the angle that that wire is in there. So the other thing you can do is you can look at the angle. And therefore then it introduces at A level the idea that F equals BIL sine theta. Okay, G May says, somebody's looked up on Save My Exams, and they say the wire will experience the force upwards due to Newton's third law. The force pushing downwards will be the mass on the balance. Yeah, so basically, if you think about, there's that wire in the field here. If that's going to be fixed in position and there's going to be a force which is either up or down, that's either going to want to pull this up or it's going to push it down away from it. Okay, and that's because of, yeah, the Newton pairs of forces. So just as much as there's a force upwards due to the wire, that's going to result in a force downwards, and that's like a kind of Newton pair, I guess. Okay, that was the end of that question. We've now got about 10 minutes left. Does anybody have any questions about that practical? Anybody got anything that maybe not so clear about? I've seen some really good questions, and what's really nice in the chat for everybody watching this live who's subscribed. And by the way, thank you everybody. It's great to see so many people here. Bramble, magnetic fields. Yeah, this is some good stuff. Okay, Gmail, yeah, you see that? That's good. We're going to be doing this question next, and I guess I just want to show this to you quite clearly about the difference between a value and the log of the value to 2 or 3 decimal places. Okay, right. Should we move on to do some stuff with log graphs? I did this the other day. Some people were a little bit unsure, but what I tried to do in this daily workout book, which has got lots of questions, I tried to sort of build stuff up day after day after day. Right, so let's look at this value here. So x equals 3.24. Now, if you take the log to the base 10 of that, of 3.24, to 2 decimal places, that's 0.51. And here to 3 decimal places, it's 0.5105454. So I guess we could say 0.511. Okay. The next one, we're going to do the log of 3.25, and here to 2 decimal places, that's 0.51. But if we look at it to 3 decimal places, it's 0.512. And this one over here, we've got the log of 3.26, and to 2 decimal places, it's 0.51. But to 3 decimal places, it's 0.513. Okay. And effectively, what we have here is information which is given to 3 significant figures. And when you've got a value to 3 significant figures, when you take the log value of that, we need to do it to 3 decimal places. If you only do it to 2 decimal places, all of these numbers look the same. And if you were to kind of go back the other way, then what we find is 0.51 gives an answer of like 3.2356. So the rule is, if you've got data given to 3 significant figures, when you work out the log of that number, or the natural log, you always give it to the same number of decimal places as a significant figure. Does that help? And maybe that kind of just helps kind of expand what we did the other day. Right, the next bit is sketch the construction of a simple step-up transformer. Label the primary and secondary coils and the magnetically soft iron core. So this one here is, I did this because this book is really for students in year 12 who are about to go into year 13. And a lot of the stuff is based on GCSE physics. And I would say that transformers at A level aren't really any more difficult than transformers at GCSE. So this is basically going to be our soft iron core. We then have on this side our primary coil. And if it's a step up, we're going to have more turns on the secondary. So that's going to be primary. And then we'd have our secondary coil on the other side. So it looks something like that. The main thing is we've got more. I've rushed it a bit. Okay, so that's our secondary thing. Okay, define gravitational potential energy and gravitational potential. So what are people saying? Gravitational potential and the energy definition seem the same. How can you tell them apart? So yeah, I reckon this is probably one of, I think, for me personally, looking at fields, I think is one of the most tricky areas of physics. Now, this definition from the 16th of August, I've got the full definition written in the back of the book. Okay, so basically gravitational potential energy is the work done to move a small mass from infinity to its position in a gravitational field. But gravitational potential is the work done per unit mass. And as Jamil Rahman says, potential is potential energy per unit mass. So yeah, basically what we have is, this is about the, let me just write it down, the work done to move a small mass from infinity to that position in the field, but gravitational potential is about the work done per unit mass. Okay, does that help, Madam Pinky? Hopefully that's helping. But so yeah, they are similar, and this is the thing where when you've spent a bit more time with some like flashcards, they kind of make sense, and you just have to know it for the next few months, and then you can forget about it for the rest of your life. Okay, but there are certain definitions that you need to know. In actual fact, so the definitions in that book I actually worked out based on real mark schemes. So let me just see if I'm logged in. Okay, so this is my website, alevelphysicsonline.com. You can see the live schedule here. At the very bottom of the page, there's something which has definitions sheets. Okay, and I'll make it clearer very soon on the website. But basically, we're looking here at fields. So I've got some definitions here, and this is like a PDF that you can download. We've got the definitions for fields, and we've got gravitational, so we've got things like electric potential is the work done per unit charge in bringing a positive charge from infinity to that point. And then of course we have I don't actually have all of them here. I'll add more bits and pieces in the future. So basically, if anybody would like to get their hands on these definitions, which have actually come from real exams, so you can look at, let's say, electricity. These are things that I've seen in exams. And again, they're not exam board specific at the moment, but you can find all of these over at A-Level Physics Online. You can just download them. You know, resistivity is the resistance of a unit cube. That's come up in a mark scheme before, and that got full marks. Yeah, let me see if I can just put that in the chat. Okay, so bear with me just for 1 second. So the definition sheets, I'll put them in the chat. There we go. So if you click on the link, that will take you to my website, and you can download all of these and sort of share them with people, test yourself. So things like electromotive force, you need to know what that is. You need to know about the kind of Ohm's law, potential divider, all these kind of things that have come up in exams before could be useful. Okay, reflecting and refracting telescope equations. Do I have something about that? I actually have. Again, I'll put up a link just within the chat. So I do have videos about all of that. So, oh, here we go. Sorry, I'm just looking on my website while I'm doing the stream. So on astrophysics, I do have a whole page of videos about telescopes. So let me just put them in the chat. There we go. So hopefully if you click on that link, you can find videos that go through the different sorts of telescopes. What I'll do as well is on my website, if you go to AQA and you click on the astrophysics option, You can see here that I've got extra videos, and I think if you click on this you can see the stuff I've got. So on telescopes I've got videos about astronomical refracting telescopes. I've got a video about magnification of refracting telescopes, Cassegrain reflecting telescopes, and then a bit about refracting versus reflecting. I've also got a bit here about radio, infrared, UV and X-ray telescopes, Rayleigh criterion, quantum efficiency, CCDs and the eye. So if you are doing AQA astronomy, then I think some of these videos could help you. I know a lot of other people, and this is something that I think a lot of people haven't seen so far, is if you are doing AQA and you're doing the option to do with turning points. So I do have some stuff here that can help you, including things like stuff to do with like wave particle duality. And again, all of these videos here could help you as you're doing this kind of last bit of year 13 revision. So if you want to find out more about electron microscopes, I've got some lovely videos. Hopefully that helps. How do you work out the grade boundaries for A-level physics? Because they do seem inconsistent. Yeah, I would say that every year the grade boundaries do change, and they basically base it on the cohort of students that come through, and sometimes you get a really difficult paper. So if there's a difficult paper, then everybody finds it difficult, and that just means that it's going to have quite low grade boundaries. But I'd say don't worry about them too much. Just if you find the grade boundaries just by Googling them, then actually just give yourself, because I guess if you're self-marking your work, it's often hard to judge if you do have the correct answer and what would an examiner have actually given you. So yeah, hopefully some of the stuff I've talked about this evening helps. Don't worry too much about the grade boundaries. The key thing is just to get to as many marks as possible. That's the main thing you need to be doing. So thank you everybody. I will see all of you again tomorrow night for another live stream, again from 7:30 for GCSE, from 8 o'clock for A-level, and I do have another video where I interviewed some students recently about their tips for exam success. You can find that on my YouTube channel. And yeah, thank you everybody. Good night, and I'll see you again tomorrow. Thanks.